welcome to the last technical tutorial that we have for you today. We are here with Philipp Danninger from one of our supporting partners, Parkside Interactive. He'll be doing a tutorial on Go with the Flow, track your machine learning lifecycle with MLflow. So that's it for me. Philipp, you can take the floor. We will be here, in the chat, and you can, if there's any difficulties or anything. So feel free to begin.
All right. Thank you very much. Warm welcome from my side. I'll just maybe go ahead and share the presentation that I have prepared for today's tutorial. So please let me know if you can. Okay. Just have to allow Zoom to take over the screen. Give me a second. I'll be right back. Give me a minute. Okay, so now I should be able to share my screen. Perfect. Now, everybody, let me know if you can see the presentation. Otherwise, I'll start. Okay, so welcome from my side. My name is Philipp Danninger, and I've prepared a small tutorial regarding the tracking of machine learning applications or machine learning projects. For this tutorial, or what we at Parkside use is the open source library MLflow that I want to present. And for today's tutorial, I have prepared the following presentation. So at first, I would like to give you a small introduction of who we are, of who my company is and who I am. Then I'll go ahead and talk about why you should, or what are the reasons for tracking an MLflow lifecycle or an ML lifecycle itself. Continue with a short introduction to MLflow itself, go into the tutorial, and then finish up with a small recap of this session. Now, so in brief, what is Parkside Interactive and who are we? We are a software development company that is based in Graz, Vienna, Linz, Porto. Sometimes we still have to San Francisco, and as of recent, we also acquired a new location in Basel, Switzerland. We are a custom software developer, for which we do from software development to research and testing, quality assurance, DevOps, but also UI and UX design, and also cybersecurity. And I am now one of the team members of the data science and AI team, where we develop several, where we are developing machine learning applications, but also develop data science use cases. My name is, as I said, Philipp Danninger. I have originally an economics background. This is how I got in contact with data analysis, and particularly with time series analysis and regressional analysis. And during the pandemic, I started a second master degree in data and information science to complete the, let's say, IT part of data analysis and focus really particularly on that. So with no further ado, I will continue now with the main topic of this session. So why are we here in the end? And I want to start with this question. So why track the life cycle of ML applications? All sorts of machine learning problems, use cases, etc., might have different life cycles, and people would design them differently. I just summarized a couple of steps that we encountered which we usually encounter when we do projects at Parkside. So the first thing is that we have to find out what kind of data ingress channels, etc. we might have, what kind of data, the size of it, is it structured or unstructured, or how often do we receive the data? Is it one chunk that we receive and have to analyze, or is it a continuous process where we get data daily? Is it a stream? Do we get it weekly or monthly? So this is these first questions that we have to ask ourselves, and how to set up everything we need for our project. The next thing is data cleaning. So what kind of parts do we usually use from the data? What do we have to throw away? How do we store the data? Do we need servers? Can we store it locally? How big are these data sizes that we have at hand, or do we store it in the cloud? So these are things that we usually then are concern ourselves with. Next is, let's say, a training set creation for a respective machine learning model. And here you, depending on the data or the problem at hand, you might use different ways of data imputation methods for missing data. Is it different sample sizes that you want to try out for training, test, or validation sets? Do you recognize a class imbalance potentially for a classification problem where you might use synthetic sampling to cover this problem? Do you have any data leakage maybe in your problem, or could this be a problem? So there are also a couple of questions that you have to ask yourself, and all of these answers or decisions that you then make have further implications on the next step, would be the model training and evaluation. Here, the main questions are regarding the choice of algorithm. So let's say, starting with a baseline model, do you want to start with a more simplistic algorithm and then continue with, let's say, more sophisticated ones? What kind of hyperparameters do you have there that you might tune during cross-validation, or try to find the best one? And then also, depending on the respective machine learning problem, which performance metric do you choose? Do you choose multiple ones? And for, let's say, each model training or run, how did these performance metrics develop, let's say? And can you achieve significant improvements from run to run? And the last step, which is for us particularly very important, because we focus on model deployment and maintenance of all our solutions that we want something to provide our customers with. And here we're mainly focused on the deployment method and the workflows. So can we do the deployment, or does the customer do it? How do we have to deliver the models, or can we connect it to an API that we then perform ourselves or program ourselves? what is the final version of our machine learning model? So on which version do we decide on? Is it good enough? Does it meet the customer's criteria or expectations? And with what kind of dependencies does this machine learning model come with? So of course, there could be more steps in between, and I'm sure that all of you guys can think of some of those as well. But during work on a project, we encountered several issues where we wanted to compare, let's say, training sets that we had, that we created. We wanted to see with what kind of hyperparameters we achieved this kind of performance. So we were always kind of tracking manually how our projects were developing. And the next big question is, let's say that you run through this entire circle, you have deployed a model at a customer site, and in 3 months' time, the customer has new data and wants a re-evaluation of the machine learning pipeline and the potential outcome that might be a better machine learning model. So can you answer all of these questions that arise throughout the machine learning project after some time when you have already deployed the model and then have to maybe retrain it? And there you might run into issues when it comes to reproducibility. So to remember all the different steps, what did I do, with what kind of data did I train this model, this algorithm, with what kind of hyperparameters? And to answer these questions, this is where MLflow comes into place, where you then decide what kind of components you want to store or you want to track and record to facilitate not just the reproducibility, but also the deployment of your models. And with this lifecycle in mind, I jumped to the brief introduction to MLflow. So MLflow is an open source machine learning lifecycle platform that has 4 main components. This is the tracking, projects, model, and registry. So here we can quickly jump into or jump to the website. And as you can see here, these 4 components really build the main building blocks of it. The tracking component allows you to record, query experiments that MLflow is built around. You can track data, you can track the config files, you can track performance matrices and parameters. The MLflow projects component is mainly a standardized format that you can use to reproduce bits of your code, show to other data scientists potentially, and give you some entry points to enter your projects or for others to enter your projects. The same for the component models. This is a standardized format to package up models, to deliver them and make it as reproducible as possible for others to really understand what you've been doing. And then the model registry. This is a, let's say, model store in which you can track, stage models potentially for production, for archive, and really have a tracking of what kind of models you've used for what kind of experiment. And if I go back to the presentation, let's do it like this. What I will be focusing on in the tutorial is the tracking and the registry part, because when it comes to the projects and models component, this is something we didn't use quite frequently so far within Parkside, because we work really closely together and we don't really have to share, let's say, trained models across borders, let's say. So I would like to continue with a brief introduction to the tracking, which is in my mind, or in my opinion, the most important component of MLflow. So some basics about the tracking. MLflow tracking is organized around the concept of runs. Now, a run is basically an execution of code bits that you have and that you want to record, or from which you want to record a couple of tracks or matrices. You can further group these runs into experiments. I will show this later in the tutorial, where I have two different algorithms as experiments for which you can then do multiple runs. What can you record? And this is now the very interesting part. So you can track the code version or the Git commit from which this machine learning run has been started from. You'd see the start and end time. This is something you can record. You can track the source. So which file, is it a notebook or is it a Python file or a Python script that executed the code or the run? You can track parameters, you can track hyperparameters, which is really important if you, let's say, as we are going to do later on, train an XGBoost model, for example. You can track all your metrics. Is it for a classification, is it maybe the accuracy, but also for regression, is it the R² error? Is it the root mean square error? And furthermore, you can track artifacts. And with artifacts, what is really useful is that you can track or store the training, test, and validation sets that you have created, and can always reevaluate your model based on those. Where do you store then all of these trackings? Well, MLflow allows for a lot of different kind of possibilities. You could either store it locally, so MLflow would create local folders in your repository, let's say, or in your directory where it then stores all of these runs. You could use SQL Alchemy compatible databases. So we're later on going to use an SQLite DB, but you could also, if you have to share all of your results, let's say globally, you can also do it on a remote tracking server. And finally, once your runs have been recorded, you can create them using the tracking UI or the MLflow API. So this is a really, really helpful tool to gain an overview and to access all of your code or all of your trackings quite easily. So these are the basics to MLflow and the lifecycle itself. With that in mind, I would quickly present the tutorial that I have prepared for today. So maybe some of you guys have already created this kind of plot yourself. It is the very famous prediction of the California house prices. I created a small machine learning pipeline, but for me and for this tutorial here, this is not the main focus to now show a machine learning or a trained machine learning algorithm that achieves very, very highly on predicting house prices. To me, it is more important to really show the capabilities of MLflow and how you can implement it. And what are we going to do with MLflow? So first, we're going to set up two experiments, one experiment per algorithm. Then we can do multiple runs for these experiments if we want to, track the artifacts, performance metrics, and hyperparameters, register a model later on, and to show how with a registered model then we can predict house prices and come up with a final model. In the materials that you can access from the or have been sent out by the organizer of this conference, I've also created a small GitHub repository You can clone it yourself and create the respective environment from the YAML file that is also in the repository itself. But to following this tutorial and based on the time that I have to show it, you don't have to code while this tutorial. So I've prepared a small Jupyter notebook that I want to go through with you guys and show the capabilities. Okay, so now it's time to actually jump in and look at this tutorial. But before I continue, are there any questions so far? Maybe I have to. See. If there are no questions so far, then I'll continue. Okay, so to start with, I have the I load all the dependencies that I need or packages, and then let's look at the data set itself. I have downloaded this data set from Kaggle. Also, the link is in this notebook, and it describes data of central blocks of Californian cities with, if you do it a little bigger, from longitude and latitude, so they're positioning the median housing age in this block, the number of total rooms and total bedrooms, the population of the block, households, median income, median house value, and a categorical feature for ocean proximity. Now, the median house value, this is what we want to predict at the end using our explanatory features. Next up, I'll continue then with, as everybody would do, probably an explorative data analysis, where I load the file, look at the head of the data and the shape. So we have more than 20,000 of these blocks. And the data set looks, from this here, looks fine. Do some descriptive statistics, where at first, or the first thing that I recognized, maybe here, the bedroom column, where you have indication of some missing values that we're going to impute later on. The heat map of the entire data frame then also shows where this is missing for total bedrooms, and the amount of it, about 200 missing values, which is fine. We're going to look at those later on. Now, for some more explorative analysis, I plotted the distribution that we can see of the most important features. Not that interested in the longitude and the latitude as it is, but what is really important and what is expected is like the median house value, where we see the majority of the data points lies within this region. And then here I expect, let's say, like a cap of the of more luxurious areas, where you have quite a lot or a bigger frequency of houses or blocks with more expensive housing. Now, the same thing can we then do for the categorical feature of ocean proximity, where you can see for island we have larger housing values. Near ocean and near bay are then in the let's say mid-range of housing prices, and inland, so the further you away, the less the costs of housing are from the further you're away from the ocean. But it also shows a significant amount of outliers, where you could do some more, let's say, feature engineering or research into. But this is something that I don't want to focus in this tutorial right now. And then Finally, we can also have a look at the map itself. And here, if we zoom in, you can see a very nice representation of these blocks. If we scroll up here to San Francisco and to Oakland, where you have higher values of the housing prices compared to Oakland, which is near Bay or near the ocean itself. But apparently it's of course more interesting to live in San Francisco potentially. Now, as I said, we have some missing values in the total bedrooms column. And if I plot a couple of correlations with the pair plot command, we can see here for the total bedrooms is positively correlated here and here. This is one is the total rooms and one is the households. And this is a small indication for me that, okay, maybe I can impute missing values using the median. Yeah, that's fine. Might skew my distribution a little, but we could also use some other features present in the data set to impute the missing values, which we are going to do real quick. I did it with two different type of methods. So the first one is an iterative imputation method. Basically, I use all the features within my data set to predict the missing values of the total bedroom column. This works fine. If I look at this table here, where it shows me no missing values in the end for total bedrooms. However, we also get negative values now for total bedrooms, which is not intuitive if we look at this feature. Therefore, I simply use a k-nearest neighbor imputer to find these missing values and replace them accordingly. And this solves this problem for me respectively. Now, with this in mind, I again add the ocean proximity categorical feature to my new data frame that has been imputed with the k-nearest neighbor imputer. And then I have to do a little change here because the encoding method that I use does not accept this sign here. So I'll just replace it real quick and we're ready to move on. So this pipeline or this okay, please repeat the beginning. I might be coming back to the beginning, but you can also look it up in the presentation that I given or that is attended that is available through the conference pages. Otherwise, you can ask me at the end of the tutorial if you have any open questions. But to continue, and now, because after this small, let's say, explorative analysis and some pre-processing that you could extend even further, I want to go into the two main functions of this Jupyter notebook that kind of set up the tracking using MLflow. So at first, I created this function, create, train, and test set. Yes, you could do this without a function, that is fine. But what I want with this is to store these train, test, and for my explanatory features X and my target Y, because this is something that I want to do for the tracking. So I want to track those as artifacts and then just return a dictionary with these train and test sets for X and Y. And if and should there no folder be available for these CSV files, I'll create a respective path for it and create the folders. So this is what this function mainly does. And now the next and following up, we are going to the prediction and the tracking of MLflow. Now, in the beginning of the tutorial or in this presentation, I told you that MLflow allows you to track your or to track everything in different methods. You could do this by tracking it locally on your computer. You could track it in an SQL compatible database, but you could also track it with a or on a remote server. Now, for this tutorial here, I want to show I am going to do this with an SQLite DB, and this, maybe if we can make this a little smaller so that you guys can see it. What this command here, MLflow set tracking URI, does is it automatically creates this MLruns DB file, and it creates a local folder called MLruns. And this 0 here and this 1 here stands for respective experiments that you track. And this is something that that MLflow does automatically for you. Now, with this in mind, I come to the next function, and maybe I zoom in here a little bit, is the create MLflow run function. Now, with this, I did set up everything that I wanted to track for this tutorial. You could extend it way further if you want to, but for I think descriptive purposes, this works fine. So for at first, I want a respective experiment name for the runs that I want to group them in. I hand over a dictionary with hyperparameters for my algorithms, give it the train test data path for the artifacts, provided with this dictionary from before with xtrain and test, as well as with ytrain and test, and then a pipeline object that is potentially from scikit-learn, because this is also allowed by MLflow to track. And the first step is to set my tracking URI, as I said before. So this command here will later on, when executed, create this local files of an SQLite DB, but as well as the local folders. Next, I set the experiment name and I create a run name. What has been quite nice practice for us is to give it a very distinctive name or a unique one, in which we combine just the prefix of MLflow run with the experiment name and then the current time and date. So this is unique then. And with this setup, we can start a first run. And I usually continue this or start this with the with statement, because if you do it like this, you don't have to specifically state that you have to end the run. So if you would do it without this, you have to specifically tell Python, okay, this is the end of my run, please end it to track everything. And in this with block, I start with the main machine learning commands that I guess a lot of you know. So I fit my pipeline on xtrain and ytrain. I then predict on xtrain and xtest. I create the train and test, and then create multiple performance matrices to compare the performance on the training set and on the test set to check whether or not overfitting might be involved or whether my trained model generalizes well. So, and I store this in my performance dictionary here. And now I start the tracking with MLflow. And this is quite intuitive and very simple. So for each key value pair in my dictionaries, I start tracking using the command MLflow log metric for all these performance matrices. I log the hyperparameters of my algorithm, or with which I have trained my algorithm with, simple with the MLflow log param command. I track all my artifacts here that I have in the train test path locally. And then I also track my MLflow model. And this can be done since I am here using scikit-learn pipeline. I use it with the additional class of MLflow scikit-learn, and I want to give it a specific path later on, which is simply called model. And with these, with this function, we can go into the 2 experiments that I have prepared and start with a baseline model of a linear regression. And at first, what this cell of this notebook does is to simply create the train and test split, create the CSV files as artifacts, creates the dictionary. Then I create a small dictionary for the hyperparameters. For linear regressions, there aren't that many, but nevertheless, I feed it into my pipeline where I have an ordinal encoder. I frequently use that pre-processing step from the feature engine package, but you could, of course, also use scikit-learn. That doesn't matter. And as a regressor, I simply use the linear regression regressor. And all of these inputs I feed to my create MLflow run function. And now if we check here, if we execute this, a couple of things have happened. Now here, the MLruns DB was created, the MLruns folder was created, and the train test data for the linear regression have been created. And here you can already see that we have a first experiment and an initial run tracked for this experiment. So perfect, this has been run through. Next, I want to do the same thing for maybe XGBoost. I create again a respective train and test data set here with a little bit larger split of 0.3 and a different random state maybe. I create a dictionary of hyperparameters that I feed to XGBoost, and then create another MLflow run to predict the house prices. Okay, it also got tracked and run through. And here again, we can see now that we have 2 experiments in our MLruns folder locally. But maybe I want to adopt something, maybe an estimators here, this hyperparameter was too low, and I run it again. Or I want to adjust maybe the subsample a little bit and increase it here and have another run. And with that, I have now 3 MLflow runs tracked for the experiment XGBoost. And okay, if I open one of these runs, I immediately see 2 additional folders. The first is the model, a folder where it tracks everything that you would need to run your trained model and fitted pipeline. And it also tracked the train and test set CSV files. But this is not the most intuitive view if you look at it locally. And where MLflow is really, really nice is that it provides you with the respective UI. And the following command can also be seen in the README that I've created for this repository. But here we basically launch the MLflow server, where we can then have a look at all our runs. I'm predicting the California house prices, and we are going and we track the performance matrices and hyperparameters as well as multiple or further artifacts. But I'm going to show these now. So this is the MLflow UI that you can hopefully see. Here you have two tabs, the experiments and the model tabs. It creates a default experiment, but also has now tracked for our one linear regression and for XGBoost. How does this look like? We can check out this for XGBoost. We have here these 3 runs that that actually have run through. If there was a problem, this would show a red X here. It shows the source where it came from and what kind of models it created. If we look at one of these runs here, it also shows its specific ID, when it was conducted, who conducted it, in this case, me. We can see the hyperparameters that have been tracked. And then you can also see the performance matrices of this run. Where here, okay, on test and train, these look significantly different. So here I would think of or might see some indication for overfitting on the train set. Nevertheless, this works well and I can work with it and really see now, okay, here might be overfitting present. What do I need to adapt to have my models generalize way better? Next, what you could as well add is a description of this run. But what is really, really nice is now the artifacts that you have. You have the ML model, you have the environment, you have the pickle file, and you have several requirements. Everything is tracked here, as well as the train and test sets that you have. They apparently have adopted this, so this really also looks really nice, and you can have an intuitive view on what kind of data this model was trained on. So now, if let's say this would have been my final model, and I have to go back to it maybe in 3, 4, or 5 months' time to retrain the model, I know exactly on what this model has been trained on, with what kind of parameters, and what kind of performances that I was able to achieve by training this model. But now, one of the most important things is as well, you don't just want to train a model, you also want to deploy it for the customer. So that customers have some impact or positive impact on their business value. Let's say in this case, as we try to predict house prices, maybe you're working or your customer is a big housing contractor or builder. They really want to see, okay, in what kind of regions, what kind of prices could I achieve for houses that I would build there? And here MLflow comes with another nice feature, and this is the model registry, which is shown on this tab here on the left side. Now, no models have been registered so far, but you could create this manually here that I name, let's say, XGBoost. And I create this name and then go back to my experiments. And then you can click on this button here with register model and select this model this model name. And boom, a first model has been registered. But what we then want with a registered model is, let's say you want to connect it to an API that triggers the model. You feed the API with the respective input, let's say in our case with input features for a new housing block in California. And the API should only use a model that is in production, not in staging, because here we might be still working or something on something. And we also do not want a model that might be also that already be in the archive stage. So only those within production is something that we want to do or want to use. Because if a model is registered here in production, we can change it. We can might retrain the model, shift it to production, and the API does not need to change in any way. So this is also quite simply done with using MLflow. What you do is, for this, I created another function, which is called registered MLflow. I give it the respective run ID, the experiment, and the stage I want to transfer it to. And this is mainly done by creating a model URI variable, where I give it the respective run, and I enter the artifacts folder model. I again set my tracking URI, which is in this case the SQLite-DB, and I use the command MLflow register model to do this. Now with this, I gain all the different model details that I have initialized in an MLflow client. And from this client, I then can transition the model stage or the model stages, let's say from staging to production, from production to archive, whatever I want. In this case, we want to do it or we want to shift it towards production. So I simply here, let's say I use this run from XGBoost. Copy it and enter it here. And then it tells me, or MLflow tells me, okay, created version of model house price XGB. This is the name that I have entered here. And if we go back to our UI, and reload, if it reloads, boom. Now here we have for the experiment house price XGBoost, we have a model registered, and this is on the stage production. So this would be then a model that we say, okay, we connect it to our API and have this one triggered every time we feed it with a new house or housing block features. You can also then have a look at it of the version 1 where it's staged yeah, there you go. Have the source run from it and have then easily can see, okay, what kind of model is it, with what kind of parameters has it been trained, and on what. So everything here is in one place. Okay, cool. But now we also actually want to do some predictions with it. But as I said, for me now, a model in production is important. So I feed it, or I want to load specifically only that one that is in production for a given experiment, and feed it with a potential feature vector for a new house. And for this, I created a new function in the notebook, for which at first I created a pandas data frame with potential vectors, values for all our features that we have trained our model on. These are completely fictional, so I do not expect to find a housing block there anyway, but I just for descriptive purposes, I've chosen those. We create it, and then we focus on the function make prediction here. So again, quite simple. What do we need to give to MLflow to obtain a prediction? Now we give it the experiment name, the stage from which we want to tag the model from, and some the new housing data we want a prediction for. we set our tracking URI, and then we load the model simply by using MLflow sklearn load model. And we provide it with a model URI in which it should take that model from that experiment in stage, in our case, production. And that's basically it. And then if you have the loaded model, which has already been fitted, you feed it with new data and then obtain a respective prediction. In this case of $117,340 US dollars. And with this, I'm at the end of my technical tutorial session. So in general, you could track, or you can be really, really creative with what you want to track, how you want to use it, how you want to package your models, and then maybe share it with other data scientists. You could track even more parameters. MLflow also allows a command that is called auto tracking or auto logging that then takes something without your doing and writes down or tracks several different performance matrices or hyperparameters and artifacts. But here, for us, this has been really, really helpful in order to reproduce our results, get back to it, further improve if we found something or found errors throughout the process, developing machine learning concepts and products. And at the end, we really, really had just a really good experiment experience with it. So if you want, just check it out. The documentation is also quite nice, I have to say. I found it very intuitive. And since I'm at the end of my presentation, feel free to ask questions, and I hope that I can answer them. I really want to thank everybody for participating. I hope that you guys are at the conference tomorrow. I'll be there as well. If you have any further questions, then also please go ahead, come up to me and just ask. But with that, thank you very much. And I'm looking forward to all your questions.
Hi, Philip. I'm not sure if you can see in Zoom. We do have some questions. I'll just get through some of the technicals.
Yeah.
One attendee asked that we start earlier than 4. Yes, we did, but don't worry. We have recorded this talk and you will get it after the conference via your email. So don't worry about that. And there's another one. I'm not sure if you actually addressed this one. What are you predicting? What are you tracking? Why? Oh, okay, you missed the start. Okay, I'm guessing that this is the same person. So the contents will be shared afterwards. Are there any more questions aside from this? Okay. I think that is it. Again, the contents will be shared. The recording is recorded, and after
there's, sorry to interrupt you, but there is one from Olena. Thank you very much for. Okay, do you have any rules that your data science team should follow when working together? Any naming conventions using of MLflow documentation? Good question. We don't really have any rules that we particularly follow. The most important rule for us is communication. So whatever you do, you know, keep it simple, do frequent communications, be as clear as possible on your Git commits when sharing code. But when it comes to MLflow, it is really up to you what you want to track, what you need for yourself, where you say, okay, I have to reproduce this machine learning model potentially for a customer in some months time, or maybe after a year, and I need to be quick to go into the code, see what I did, understand it, and then take on from there. If you need to track more, you can track more. If you need to track less, track less. I mean, I here now tracked artifacts for training and test data sets, which are CSV files, and they are very small. If you work on some larger data sets, this might not be so easy. So depends on what you want to do, but also depends on what kind of storage capabilities you have for MLflow. But you can be really free when it comes to these kind of decisions.
I saw one question before, Elena. Did you also use some different programs for tracking the workflow? If yes, what have been some advantages, disadvantages?
I have not come over a different one. MLflow was the first one that we tried out. But what we did before was to write or to create functions that would write these performance matrices into CSV files. And we do then compare line by line for each training run that we did. And we were really, it worked, but we were annoyed about it a little bit because it was not that intuitive and you did not really have a lot of observability there. And then we, did some research and found MLflow. And compared to this approach, it was way better, way more intuitive. And I guess MLflow is not the only one that you can use, but I haven't come or have not researched a different one.
I would just like to say I see there are like 3 more questions, but
Yeah.
in the how should I say, the time slot for this technical tutorial, we have predicted up to 5 p.m. So feel free to go through them and like continue. Sure. Robert Lasser here could be next.
Okay, would you recommend using MLflow for your whole data pipeline or mostly focus on tracking your model fitting experiments?
I like the possibility to have this outside and maybe add more steps at a time, depending on what the machine learning problem requires. You can do it as well within an MLflow block, but I like this stepwise approach because I like to build these functions for one purpose, and in this case, just the tracking of MLflow. So this is where I would or this is how I would do it. But you can do both. This is really up to you or your preference.
How does MLflow deal with data coming from databases, especially if the source table are larger?
This depends on how you store your artifacts. I'm not quite sure now what type of art or let's say data formats you can track there as well. But MLflow, what I know is that the community is great. They develop or do releases quite frequently. And should you have any need or requests, they are quite fast and not just in answering, but also in development. So you could for sure do store other artifacts or types of artifacts as well. And then, it depends on how large the data is, of course, and that depends on where you want to track those or what kind of tracking capabilities you have. If you only do it locally, well, you might run into trouble at some point if data sets are bigger, or if you do some video classification models, this then might be done with a different, or this might be better with a external tracking server or maybe something in the cloud. And MLflow offers quite nice capabilities there.
Would CML and other PyCaret help with experiments?
Sure, could. To be honest, I haven't worked with PyCaret before, so this question I cannot really answer. Oh yeah, you saw. Yeah, I do work with Azure DevOps for a different client of mine. But I'm not sure or haven't yet combined MLflow with Azure or the Azure stack. But this is something that might be interesting for me as well. So thanks for the hint. I'll try to check that out. How much capacity is needed approximately for storing a model? This depends on the model, I would say. If you have to train a linear regression model, I guess the pickle file might not be that large. But I attended the PyCon Berlin this week, and there I saw quite a nice talk about two guys from, I think they were from Karlsruhe in Germany, who stored really, really large random forest models. They were like 1.2 gigabyte large, and they could reduce their size quite significantly. But nevertheless, I think this really depends on the size of your model or the pickle file there.
Are you also including the experiments from MLflow in your Git repository, or are they ignored there?
They're ignored there. So because if you run the repository or the Jupyter notebook itself, these experiments will be created for you as well, so you can do this on your own. I didn't really think that this would be quite necessary to be on there, and I wanted the repository to be quite slim in this case. Are there any further questions? If not, as I said, I'll be in Vienna tomorrow. Come and say hi. I'm more than happy to chat, to talk about this topic, about others, about what kind of machine learning or data science projects we do. And yeah, feel free to add me on LinkedIn or drop a mail, and I'll try to get back to you as soon as I can.
Okay. Thank you, Philip, for this wonderful tech tutorial. And with that, I would like to announce that today's technical tutorials are coming to an end. As Philip said, all of your attendees and ticket holders. So hopefully we will all see you tomorrow at the live event, where we have, the form of, smaller talks with less technical depth. As mentioned before, these will be sent to you because they're recorded. And with that, thank you very much for attending these talks. If you did not see in the chat, you also, as ticket holders for Data Science Conference DACH, get free access to technical tutorials for our upcoming events, which are Data Science Conference Adria. So use the promo code or just write back to us directly via the support mail. And by that, I would also like to announce registration for tomorrow's event are out from 8:30. The opening of the conference is at 9:15. So that's something to keep in mind. Thank you very much again, Philip, and we'll see you guys tomorrow.
Thank you very much, everyone. Bye.